Okay, in this video we're going to look at how to graph exponential and logarithmic functions. This is a basic exponential function, and this is, in case this is hard to see, this is the function f of x is equal to a to the x, where a is the base, and in this case the base is greater than 1. So that's the conditions we're looking at. And so the base is always going to be positive, and it will never equal 1. I mean, it can equal to 1, but if it equals to 1, then it's just a horizontal line. So we look at the conditions where a is greater than 1, or when a is down here. We'll look at the same graph. This one is f of x is equal to a to the x, but in this case, a is between 0 and 1. The base is between 0 and 1. So for this exponential function right here, where the base is bigger than 1, it looks like this, and you can verify this very easily with a graphing calculator, but I'm doing this generically for a base that's bigger than 1, and it will look like this. It will always have this horizontal asymptote right here on the x-axis. It has a horizontal asymptote of y equals to 0. It will have an intercept, a y-intercept right here at the point 0, 1. It will hug the x-axis here, and it will begin to increase, and it will look something like that. That is the look of every exponential function that does not have a transformation going on where the base is bigger than 1. So the domain is from all real numbers, negative infinity to positive infinity, and the range is as close as it can get to 0 to infinity. So the range is all positive numbers, 0 to infinity. Now, what is the difference if and when the base, so all the graphs that would have the same shape to them would be anything that's got a base bigger than 1. So for instance, if you were to graph f of x is equal to 2 to the x, it would have the same basic, we could say all these same features about this. Or e to the x, because e is a number bigger than 1, 2.7, or 3.5 to the x, or 10 to the x, or pi to the x. Any of these would have these same features right there. Down here, let's consider the exponential graph where the function, the base is less than 1, but it's positive, so between 0 and 1. So we could consider maybe, this is what this one will look like. It will still have the y-intercept here at 0, 1. It will still have a horizontal asymptote right here, y equals to 0. Those things are the same. The domain and range are the same, but this time, instead of it being an increasing graph, it's a decreasing graph. And so it's going to be over here, it's up, and then it's going to come down, and over here is where it's going to begin to hug the x-axis, and this is what this will look like. So the domain is still negative infinity to positive infinity, and the range is still 0 to infinity, but in this case it's decreasing. And you see this a lot when you do applications. So when the we talk about a growth and decay factor, when the growth factor k is positive, then you basically have a positive a base bigger than 1 being raised to a power. When the growth factor is negative, then you're taking a base, we're taking e, which is a number bigger than 1, raising it to a negative number, which means kind of 1 over e to that number, which makes it a base between 0 and 1. And that's why in decay problems we see the numbers decreasing. Okay, let's go over here and talk about a logarithmic function. So just in case you can't see what I've written there, this function is f of x is equal to log base a of x, and this is the condition where a is greater than 1. Let's look at this graph. Okay, well, when the base is bigger than 1, this is what a log graph looks like. It has a vertical asymptote along the y-axis. So this is x equals to 0 is the equation of the vertical asymptote here. Instead of having a y-intercept like the exponential function, it has an x-intercept right here at 1, 0. And so it hugs the y-axis, and then it goes like this. That's the basic look and shape of a logarithmic function where the base is bigger than 1. The domain is from 0 to infinity, so we notice that you can only put positive numbers into a logarithmic function. That argument x has to be positive. in the range, you could get negative infinity, positive infinity. You can get all kinds of numbers out of a logarithmic function. So this graph is increasing, and this is what it looks like when the base is bigger than 1. Down here, this last graph, this is for f of x is equal to log base a of x, but in this case, the base a is between 0 and 1. And so when the base is between 0 and 1, it looks like this. It still has a vertical asymptote right here at x equals to 0. It still has this x-intercept here at 1, 0, but this time it hugs the y-axis up here, and then it starts looking like that. All right. And so this is not a very pretty graph, but that is what it looks like. Okay, so the domain is still 0 to infinity. The range is negative infinity to positive infinity, and the vertical asymptote is x is equal to 0. So many times students will ask me, well, what if you had over here, like, what if a was negative? Why can't a be negative? Well, if we want a to be negative, you can handle that. We handle that with transformations. Negatives visit graphs in the form of reflections. So like if we had negative e to the x and we wanted to graph that, that would be a reflection across the x-axis. Or if you want it to be part of the base, negative a, negative e, negative 2, if that's your base, that would be a reflection across the y-axis. So that's what we're going to discuss in the next video.